Hello everyone, welcome back to the course Vector Calculus and Complex Analysis. Myself Dr. N.CH.Ramgopal, working as Associate Professor in Mathematics in the Department of Humanities and Sciences, MLR Institute of Technology, Hyderabad. Today, I am going to continue the same topic that we have discussed in the last video, the evaluation of definite integrals of this particular type. So, that's why this is part 2 of the same topic. And the procedure is the same as we discussed in the last class. We use the transformation z equal to e power I theta and d theta is dz by iz, and then we write cos theta and sin theta in terms of z e power iz plus e power minus iz by 2 and e power iz minus e power minus iz by 2i. So, we transform the function of theta into function of z, then we find the poles and residues, and with the help of residue theorem we can evaluate the given line integral. So, let us discuss one more problem on the same topic. Here, show by method of residues, the line integral of this is equal to pi a by root a square minus b square power 3 by 2. So, coming to the solution part, here the LHS is integral 0 to pi d theta by a plus b cos theta whole square. So, use the transformation z equal to e power I theta. From this, by differentiating on both sides and simplifying, we get d theta is dz by iz. And here it is involving cos theta. So, use e power I theta plus e power minus I theta by 2. Then this LHS becomes, along the curve C, 1 by a plus b into, and here e power I theta is z, and then e power minus I theta becomes 1 by z by 2. So, by simplifying this, we get z square plus 1 by 2z. So, z square plus 1 by 2z here, and whole square, d theta is dz by iz. So, here 1 by I we can write outside, then by taking the LCM here, 2az plus b into z square plus 1 whole square by 4z square, and here dz by z. So, 1 by I into this 4z square comes to the numerator, 4z square by 2az plus bz square plus b whole square dz by z. So, 1 by I into integral C, or we can write this 4 also outside the integral. So, 4 by I into integral C, z and square gets cancelled, z by bz square plus 2az plus b whole square dz. And then this is equal to 4 by I into integral z by, I will take b common. So, that comes b square comes out, z square plus 2a by b z plus 1 whole square dz. So, 4b square I integral of f of z dz. This is in this form, integral f of z dz, where what is that f of z? Z by z square plus 2a z by b plus 1 whole square. And to take the help of residue theorem, first we need to find the poles. How to find the poles? By equating the denominator to 0. Z square plus 2a z by b plus 1 whole square is 0. That implies z square plus 2a z by b plus 1 is 0, which is a polynomial of degree 2. So, therefore, by finding the roots, we get z equal to minus a plus or minus root a square minus b square by b. So, here there are two roots. Let us consider the first root minus a plus root a square minus b square by b as alpha, and the second root minus a minus root a square minus b square by b as beta. And here the condition is given, a is greater than b is greater than 1. Here the condition is given, a is greater than b is greater than 0, a greater than b greater than 0. Therefore, it is very clear that modulus of this b value, beta value is greater than 1. modulus of beta is greater than 1. And we know that mod alpha into beta, that means the product of the roots must be equal to 1. From these two, we can say that mod alpha is less than 1. Therefore, alpha is the only pole that lies inside the curve C, the unit circle. So, it is enough to find the residue at this alpha. So, residue of F at Z equal to alpha. So, here alpha we have square. So, alpha is a pole of order 2. So, therefore, A equal to alpha and M equal to 2. We have the formula to find the residue of a pole of order M. Residue of F at Z equal to A, which is a pole of order M. 1 by M minus 1 factorial limit Z tends to A d power M minus 1 by d Z power M minus 1 Z minus A power M F of Z. So, we use this formula to find the residue of the function at Z equal to alpha. What is that? M equal to 2. So, 2 minus 1 factorial, which is 1 factorial 1. So, simply limit Z tends to alpha d by dz of Z minus alpha into F of Z. What is F of Z here? So, Z by, and this can be written as Z minus alpha into Z minus beta. So, here alpha is a pole of order 2. So, power M is 2. So, whole square, and here these two gets cancelled, and limit Z tends to alpha, we need to differentiate this Z by Z minus beta whole square. And what is the derivative of this? Limit Z tends to alpha, U by V rule. So, Z minus beta power 4, denominator into numerator derivative 1 minus numerator into denominator derivative 2 into Z minus beta. So, by simplifying this, we get limit Z tends to alpha. I can take Z minus beta common here, so that 1 minus 2Z remains by Z minus beta whole square. Therefore, the residue of F at Z equal to alpha is equal to limit Z tends to alpha. Here I can take Z minus beta common, then one more Z minus beta left, and here Z minus beta common minus 2Z. Minus 2Z by Z minus beta power 4. So, this 3 times. And now, limit Z tends to alpha, this is minus beta minus Z by Z minus beta whole cube. Now, taking Z tends to alpha, we get minus of alpha plus beta by alpha minus beta whole cube. And what is alpha here? Minus A plus root A square minus B square by B, and beta is minus A minus root A square minus B square by B. So, alpha plus beta becomes minus 2A by B, and the second term gets cancelled. Alpha minus beta, so here this becomes plus A by B. So, these two cancel, 2 times of the second term. So, therefore, the residue is equal to minus, and here we have minus sign and here minus sign. So, 2A by B into 1 by 2 root A square minus B square whole cube by B cube, that comes here. So, that implies this is 2A B square by whole cube 8 A square minus B square power 3 by 2. So, 4 times. So, the residue is AB square by 4 into A square minus B square power 3 by 2. Now, we use the Cauchy's residue theorem to evaluate the line integral of that f of z. So we have the LHS is 4 by b square I integral c f of z dz, which is equal to 4 by b square I into 2 pi I into sum of the residues. So this is 4 by b square I into 2 pi I into, we have only one residue. So where that residue is a b square by 4 into a square minus b square power 3 by 2. So by simplifying this, b square gets cancelled, I gets cancelled, 4 gets cancelled, 2 pi by 2 pi a by a square minus b square power 3 by 2. So this we have calculated for 0 to 2 pi. 0 to 2 pi, the answer is 2 pi a by a square minus b square power 3 by 2. So for 0 to pi, this becomes 1 by 2 into 2 pi a by a square minus b square by 3 by 2. These two gets cancelled. So pi a by a square minus b square power 3 by 2. So which is RHS. And so we can use the same integral 0 to 2 pi d theta by a plus b cos theta whole square is equal to, for 2 pi a by a square minus b square power 3 by 2. Here we need to evaluate this. So compare with the standard form, a equal to 5, b equal to minus 3. Then 2 pi a is 5 by a square 25 minus b square 9 power 3 by 2. So 10 pi by 25 minus 9, 16. So which is 4 square power 3 by 2. So 10 pi by 16 into 4. So 5 pi by 32. So in today's session, we have discussed about a method of finding the line integral of a function involving trigonometric functions. So from 0 to 2 pi or 0 to pi. If you calculate from 0 to 2 pi, then divide it by 2 to find from 0 to pi. This is for today's session, and we will meet in the next session. Thank you.